We're going to be looking at several optimization problems this morning. I've got 4 planned for us. We'll start half of it today, and then we'll finish up with the other half on Monday. This is one of those topics that is one of the reasons we really care about calculus. It's one of the more important applications to come out of this course. It's not something that I felt like putting on a skills quiz. So even though it's not on a skills quiz, it is still going to be a major part of the third exam. You can expect 1 or maybe 2 optimization questions on that exam. These are sort of word problem style questions. You'll definitely have one of these on the final exam as well. When I think about calculus, I think about first and second derivative test. I think about derivatives. I think about optimization. Those are the 3 big things to come out of the course. So let's take a look at a couple of problems together. This is really one of those topics that you want to read through the textbook. I haven't used any of the textbook examples here. So there are several examples in the textbook. There will be several examples that we'll go over in class. And then there are videos that have additional examples as well. So let's start with this first example. And much like we did related rates back when we were doing related rates problems, there's going to be kind of a format that we're going to follow for how to talk about and do these kinds of questions. I want you to start out by trying to draw the picture here. I think it's good for students to try to draw the pictures for these problems before I start working them. So I'm going to give you about 2 minutes here to draw what you think the picture is that represents this problem, and then we'll look at it together. All right, let's take a look at the picture for this problem, and then we'll discuss it together. They're planning to enclose a 3,000 square foot rectangular region in a botanical garden. So we've got a rectangle. And we know that 3 sides of the rectangle are going to be shrubs. So we're going to have shrubs on 3 sides. And we're going to have fence on the other side. All right, what we know is that a rectangle has sides X and Y. So since they're different lengths, so if this side is X, then I'll call this side X as well. If this side is Y, then this side will be Y as well. So based on what the problem says, it says that they will use shrubs that cost $15 per foot along the shrub sides and $10 per foot along the 4th side. So step 1 to these problems is always going to be to draw a picture. Most of these problems have some sort of picture element to them. So draw a complete well-labeled picture. Okay, the second step is from that picture, determine your objective function. And any constraints. So the terminology, the important terminology that I'm introducing here is what's called the objective function and what are called the constraints. And almost every single optimization problem will have, well, I think all of them actually will have an objective function. Your objective in this problem is to minimize cost, right? And it'll be subject to some constraint. So let's look at what it is for this particular question. So my objective is to minimize cost. And my cost function here is going to be a function that involves both X and Y. If we were to write it out, it would be let's see here, the fencing is $10 per foot. So it would be 10 times Y. That represents the cost for this bottom half, where Y is the number of feet. So yeah, you should probably write off to the side, X is the number of feet. Y is also in terms of feet. So we've got $10 times the number of feet. So $10 per foot times the number of feet, $10 for the fence side. And then you have $15 per foot on the other three sides. The other three sides are 2 X's and 1 Y. So this would be our cost function. This is what we call the objective function. But as it stands right now, this function is a function of both X and Y. In fact, if I was to simplify it out here, you've got 10Y and 15Y, so that's 25Y. 15 times 2 is 30X. So right now, this function is a function of both the variables X and Y, which means in this course, we can't really do anything with it at this point. All the problems that we've looked at this semester where we've taken derivatives or done things like that were functions of one variable, not functions of multiple variables. If you want to do optimization for multiple variables, that will be in Calculus 3 is when you'll take that on. So what we need to be able to do here is somehow come up with a substitution for either the X variable or Y variable so that this is in terms of just one variable. So this is your objective function. And it's the constraint in the problem that'll help you narrow it down to a single variable. So what is constraining X and Y in this problem? Is there some other piece of information that I know that constrains the values of what X and Y can be? Does anybody have a suggestion?
Would one of our constraints be that we're trying to find the cheapest costs?
Yeah, that's part of the objective, actually. That's our objective. So we're trying to minimize this function. But when I say minimize this function, minimize over what, right? So even when we did, absolute maxes and min problems, we had intervals that we were trying to do that on. Now, I'm not saying we necessarily have an interval here, but there's some sort of constraint here that's going to let us figure out X in terms of Y.
3,000 square foot rectangle?
Yeah. So my constraint here is I know that X times Y, which is the area of that rectangle, must be 3,000 square feet. Since I know that's my constraint, I can use that to solve for, say, Y in terms of X. So Y is 3,000 divided by X. And I can take and plug that in to my cost function. So now my cost function will be just in terms of X, and it'll be 25 times 3,000 over X plus 30X, or 75,000 over X plus 30X. Okay, at this point, that is step 2. I've determined my objective function. Here's my objective function in a good form. I know what my constraints are, and it's just a matter of, at this point, figuring out what the value of x is that will minimize this function. So we know how to do minimization. Minimization, so step 3 is minimize or maximize, depending on the problem, the objective function by setting, in this case, c prime of x equal to 0 and finding the critical points. So after you have your objective function, the next step should always be to take the derivative of the objective function, set it equal to 0, and find critical points. So the derivative of this function will turn out to be negative 75,000 over x squared plus 30. I'm going to set it equal to 0. So I have 30 is equal to 75,000 over x squared. So 30x squared is 75,000, and x squared is 75,000 divided by 30. So x is the square root of all of that. Now, normally when we would do this, we would do plus or minus the square root. But remember, x is distance in feet, so it doesn't make any sense to talk about the negative answer here. So we'll just dive into Desmos real quick and get that value. And so I get that that is 50. So x here is 50. All right, so if I know x is 50, then what I have to determine is, it's at this point, all I know is that x equal to 50 is a critical point. I don't know whether it's a maximum or a minimum. So there are many ways that we could figure this out. The easiest way is, in this case, is to use second derivative test. So if I do second derivative test, what I can do, and so this is step 4. Step 4 is determine if critical point is a max or min, or could be neither. And the easiest way to do that in this case is to compute one more derivative. So if I take my derivative and compute another derivative, the second derivative of this cost function will turn out to be, let's see here, that would be positive 150,000 over x cubed. So that's the second derivative. And the second derivative test says if you evaluate the second derivative at the critical point, whether it's concave up or concave down tells you whether you have a max or a min. So if I plug 50 into this, you can clearly see that that's going to be positive. So if your second derivative is positive, then the graph turns up, which means any critical point you find will be a minimum. So I know that x equal to 50 is a minimum for this problem. So step 5, interpret and give final answer. So the final answer here will be both the value for x and the y. So we're going to interpret and give our final answer. What you want to do then is, if I know x is 50, I can go back to the constraint. Remember, the constraint back up here is where y is 3,000 over x. So I can plug in 50 to get the y value. So if y is 3,000 over x, it's 3,000 over 50, which looks like it is 60. So I know that this rectangular garden is going to have to be 50 by 50 by 60 by 60. So those are the dimensions that are needed. So it says find the minimum total cost for erecting a perimeter of this region. So I haven't actually answered the question yet. I know what the dimensions need to look like, but my minimum cost is what we're looking for. So if you want to minimize cost, I'm looking at that cost function when X is 50. If I plug it back into the original cost function, then I'll get a cost of $4,500. So there's the answer to the question. The minimum I can do this for is 4,500, and that's if I build the rectangle 50 feet by 60 feet. So I'm plugging the 50 back into the original cost function. So going back up here to this function right here, this is what I plugged the 50 into. All right, are there any questions over the kind of format that we're following here, like the steps that are involved? Because the steps aren't going to change. The math and the setting will change, but the steps really aren't going to change from question to question.
Where did the 150,000 come from? Where C double prime?
Right here, yeah. So that I took the derivative. So you can see here, C prime is negative 75,000 over x squared. When you do the power rule, this is negative 75,000 x to the negative 2. So its derivative is negative 75,000 times negative 2, which is 150,000 x to the negative 3. So if if you take the derivative, that's what you would get.
So you don't have to find anything, since if you set x equal to 0 on the original function, you get I think you get like an asymptote there that you don't have to evaluate that at all.
Well, no, because for starters, x equal to 0 practically here means that you don't have a rectangle, right? So you always have to think about practicality. That's always one of your constraints, by the way, is things need to make practical sense. Like I can't be talking about negative values for any of these variables. And I also can't let x be 0 or y be 0, because then I simply wouldn't have a rectangle. So one of the constraints here is that x be greater than 0, y be greater than 0. That's a constraint in addition to the constraint for the area. All right, let's do some more examples. All right, so this next problem, I want to fit a rectangle inside a semicircle of radius 2. What's the largest area the rectangle can have, and what are its dimensions? All right. So this is a very common kind of optimization problem. It's called an inscription problem or inscribing problem. The basic idea here is that we have, the picture is what's going to be helpful here. We have a semicircle of radius 2. And it doesn't give any units, so I'm not necessarily interested in the units. We could give it whatever units we wanted to, but semicircle of radius 2. And the goal of this problem is to fit a rectangle inside that semicircle. So for example, I could put a rectangle that goes here. Or maybe I could put a rectangle that goes here. Inscribed simply means that it must fit within the semicircle. I could make another rectangle that goes here. Right? So all of those are rectangles that are inscribed, and what the question is asking is, out of all possible rectangles, which one has maximum area? So that's what the question is asking. And at first it may seem like, how on earth are we supposed to do that? So let me just look at one rectangle with you. All right, so See if I can draw this in. Oop, that's not what I wanted. There we go. All right, so we've got our one rectangle here. It intersects the curve there and there. Now, it doesn't matter that I'm drawing a specific rectangle in here. I just need something for guidance purposes to help me explain what the math is here. So I know this distance. This distance is 2 because it's part of the radius. So I automatically know that. And if I call this point where it makes an intersection the point x comma y, that's also going to be helpful. So I know I've got some intersection point x comma y, and it makes the most sense to call this point here at the center of the semicircle, to call that the origin 0, 0. So I'm sort of laying out a coordinate grid to kind of help me with this. Now, since I know it's a semicircle of radius 2, then I know that this is the graph x squared plus y squared equals 2 squared, which is x squared plus y squared equals 4, which if I solve for y, y is plus or minus the square root of 4 minus x squared. Now, which one is it here? The way I have this drawn, is it the positive or the negative one?
Positive?
It's the positive, right? The upper half of the circle is the positive y because it's above the x-axis. So it has positive y values. So I know that my answer here for what the curve is y equal square root of 4 minus x squared. So this is kind of a good start in terms of what we would want to do.
Could you include if you decided to do like the lower half, could you include the negative?
Yeah, if I drew the semicircle upside down, then yeah, I could use the negative half. And the answer, by the way, is still going to be the same. Because it's just flipped, but you're still going to get the same area and everything. So let's talk about the rectangle itself. So my goal here is to maximize area. And area in this case is length times width. What is the length of that rectangle? So length is
2x.
Horizontal distance. It's 2x. Very good. Since I made this the coordinate xy, then this distance here is x, and this distance here is y. So I know that my rectangle has length 2x, and it has width, the height, which would be y. But I just came over here to the side and used the fact that my rectangle is constrained by the semicircle. So this is your constraint over here. I use the fact that it's constrained by the semicircle to tell me that y is square root of 4 minus x squared. So I use that constraint to update my objective function. And so now my objective function is just a function of x. And so this is my objective function. Now, one of the things you should ask yourself anytime you write down an objective function like we've done here, is there some constraint in addition to the ones we've already used on the variables involved? Meaning, is there a limit to what I can make x? So if you look, x is this half distance here. What range of values must x take on? For instance, can x be 2?
No.
Yes.
I mean, technically it can, but you get a rectangle having 0 area. So it's clearly going to be a minimum. The same thing is true if x is 0, right? If x is 0, then you just get a line pointing straight up and there's no width or there's no length to it. So there's no area. So, you know, you can say 0 less than or equal to x less than or equal to 2 because technically 0 and 2 would work, but we know that they're not going to maximize the area. They'll actually minimize the area. So this is the interval that we're doing our calculations on. So this is back to 2 weeks ago where we were maximizing or minimizing functions on an interval. You've got a function and I need to maximize it on this interval. All right, so we're going to start by taking the derivative. So the derivative of this function, I'm going to use power rule to do that. So the derivative of the first, which is just 2 times the second function, or excuse me, product rule, plus the first times the derivative of the second. So the derivative of the second function here is negative 2x, that's the inner derivative, divided by 1, so 1 over 2 square root 4 minus x squared. All right, so simplifying this a little bit, this is 2 square root 4 minus x squared. Let's see here, the 2's here cancel. So you're left with minus 2x squared over square root 4 minus x squared. All right. So I've set it equal to 0 because I want to find my critical points. There is a way to do this to make your life so much simpler here. Algebraically, what should I do at this point to make this a much easier problem to work with?
You should get
Common denominator.
Common denominator is actually okay, but it's still a little bit of overkill. Notice I've got the same square root here that I have here. So if I multiplied through by that square root, then I can make this much simpler. So if I multiplied by square root 4 minus x squared here, multiplied by square root 4 minus x squared here, multiplied by it here, right? So I multiply through by that square root. You can see a square root times a square root. Well, that cancels the square root. So you're left with 4 minus x squared. And then here, when you multiply it by the square root, those cancel. So you're left with minus 2x squared. And 0 times the square root is just 0. So if you multiply through by that square root, this ends up looking very nice. So you get 8 minus 2x, so it's 8 minus 4x squared is 0. So 8 is equal to 4x squared, or 2 is equal to x squared. So x is, once again, plus or minus the square root of 2, but only the positive square root of 2 makes sense. So I am confident that this is going to be my maximum. The reason that I'm confident is on an interval, you only need to check your critical point, which is square root 2, and your endpoints. And we've already remarked that both of the endpoints are going to give us a rectangle having 0 area. So I know that this has to be the maximum based on the closed interval test. So if I know x is square root of 2, then I know y is square root of 4 minus x squared. So this is what square root of 4, that's just square root of 2 is square root of 2 as well. So I know that both x and y have to be square root 2, square root 2. Now, we haven't actually answered the question completely, because even though these are the dimensions that the rectangle would have to be, well, the dimensions are technically, it would have a length of 2 square root 2, and it would have a height of square root 2. So even though these are the dimensions that it would have to be, the area we have not answered yet. The area of the maximized would be length times width, or length times height, length times width, which would be, looks like 4. So whatever our units are here, like 4 feet squared, meters squared, whatever. So we know that these are the dimensions and that this would be the area. All right, let's see if I can fit that all on the same screen there. Do we have any questions about that process that we took on this problem?
Is the in problems like this, is the dimensions usually a square, or do they change a lot?
Yeah, so this isn't quite a square, but it is going to be a special angle here, right? So if you actually calculate the angle here, because the length is twice the width, one side is twice the other, that's a 60-30 triangle. So this is going to be a 60-30 triangle that's formed right here. Or actually, no, I have that wrong. Sorry, since this is square root of 2 and this is square root of 2, I thought it was, yeah, the whole thing. This would be a 60-30 triangle, but this is actually 45 degrees. So it is square on this half, right? So it's 2 squares. So this is actually a 45-degree angle.
Oh, that makes sense.
Yeah, so this is a 45-degree angle here. And yeah, the 45-degree angle is the one that will maximize area. Squares tend to maximize area. So as square as we could make this is to make it a sum of 2 squares. And so that maximized the area here. All right, I want you to try one to see if you can come up with the objective function on your own here. And so I'll give you a couple of minutes to try to figure this one out, and then I'll let you respond with the one that you think is correct. So here we have a cylindrical can, think like a Coke can or something. Well, it's going to be much bigger because it's meters cubed, but a can that holds 20 pi meters cubed. So that's the volume of the can. The material for the top of the can is $10 per square meter. The material for the sides of the can are $8 per square meter. So which of these is the correct objective function if our goal is to find the height and radius of the can that is most economical? In other words, minimizes the cost to produce the can. All right, I'll give you a good couple of minutes to think about this. The code's there at the top if you need it. All right, I think I can give you about another minute here. See if you can come up with the objective function. All right, so here are our results. We're a little split. The correct answer turns out to be D. Let's take a look at it. I think here are the basics of this problem. I don't think anybody would struggle with what I have written on here so far, unless you didn't know what the volume of a cylinder was. So the volume of a cylinder is the area of the base, since it's a circular base, pi r squared times the height. So we know that, this is the height, and this is the radius. So we're told in the problem that the can must hold 20 pi meters cubed. So the volume must be 20 pi. We're going to use this as our constraint here in a little bit. We also know that our objective function is to minimize the cost it takes to produce the can. Our cost here is $10 per cubic meter, and the cubic meters are for the top and the bottom. Those are the ones that cost $10. So we'll have to figure out what the area of the top is and what the area of the bottom is. And then it's $8 per cubic meter for the area along the side. We call the area of the side the lateral surface area. So $8 per cubic meter for the lateral surface area. All right, so let's talk about the top and the bottom first. I think it's not too bad here. We know that the top and the bottom are both going to be pi r squared. So if I'm updating my cost function here, it's $10 times pi r squared plus pi r squared, so 2 pi r squareds. Okay, and then it's going to be $8 times the side. Now the side is the thing that may give you a little bit more problem. But imagine it this way. If you were in the grocery store and you had a canned good, like I don't know, canned green beans or whatever, and there's a label that surrounds the outer side of the can, what shape does that label make if you were to peel it off?
Rectangle?
It's a rectangle. So it's the same thing here. If you take the label off the can and open it up, then what you will get is the surface area of the can, which turns out to form a rectangle. My question is, what are the dimensions of the rectangle that would be formed? Well, this side here is the height of the can as you peeled it off. So this would be H. And then the long length here is the length of the label being wrapped around the can. So this would have length equal to the circumference of the base. And the circumference of the base is 2 pi r. So the area of the label would be 2 pi r h. That's the surface area of the side. So here's my cost function, but the only problem with my cost function is it is in terms of both h and r. I have two variables here. So this is where my constraint comes in. I can use the constraint to solve for h, plug it in so that this is just in terms of r. So this constraint is 20 pi divided by pi r squared is equal to h. So that implies that h is 20 over r squared. So I can plug that into my cost function. So my cost function as a function of just r is 10 times 2, which is 20 pi r squared, plus 8 times 2 is 16, times 20 is 320. So this will be 320 pi over r once all that's multiplied through. Because you've got, well, let me do it in steps. You've got 16 pi r h is 20 over r squared. So 20 pi r squared plus 320 pi, and then you've got one r in the top cancels with one of the r's in the bottom. So this is my objective function, which was answer choice D. So now I must minimize that function because I'm trying to find the minimum cost. So minimize that function over r. So we're going to take the derivative of that function. So starting with the first part here, this is just power rule. So 2 times 20 is 40 pi r. And then here, this is 1 over r. So the derivative of 1 over r is minus 1 over r squared. So this is going to be minus 320 pi over r squared. So we'll set this equal to 0 to find the critical point. You could get a common denominator here, but remember the trick that I was talking about before where you just multiply through by r squared. I think that's much easier. So if you multiply through by r squared, this is 40 pi r cubed minus 320 pi equals 0, or 40 pi r cubed equals 320 pi, or r cubed is 320 pi divided by 40 pi, which is 8. So r cubed is 8, which means r is 2. So we know that our radius is 2. We do need to check whether or not this is a max or a min. So there are many potential ways to do that. You could create a sign chart. So I'm looking at C prime, the cost, and I'm looking at my critical point 2, and I'm going to test on either side of it. Oh yeah, did I mess up the denominator on answer choice D? Sorry about that. I'm just realizing. Thanks for pointing that out, CJ. I just realized that it had the wrong value in there. Okay. All right, so if you're testing on either side of the critical point 2, so looking here at my derivative function, I could plug in values, so I could test at like 1. So what is my derivative at 1? Is it positive or negative? Well, if I plug 1 in, I get 40 pi minus 320 pi. That's clearly going to be negative. So I know I'm decreasing over here. And if I plug in, say, like 3, 3 times 40 would be 120, but then I would be dividing that by 9, which is going to be less than 120. So this would be positive. So I know I'm going from decreasing to increasing, which means by the first derivative test that this is a minimum. So I have a minimum at the point 2, which is exactly what I want because I'm trying to minimize cost. So let's see here. To completely answer the question, it wants the most economical, right? So find the height and the radius of the can that's most economical. So I have the radius. If we go back to the constraint that I have here, 20 over r squared is the height. I can find the height using that. So the height is 20 over r squared. R is 2. So the height is 20 over 4, which is 5. So I've got my height and I've got my radius, and I can find the cost. So the cost function we have of a radius 2 is 20 pi r squared plus 320 pi over r. So let's double check here. Okay. So this value turns out to be approximately, well, not approximately, it is 240 pi, which is approximately $754. So $754 is the lowest cost they could get for this kind of can. Now, this isn't a can in the supermarket, so this is like a holding tank or something that they're making, but that's the best that we would be able to do. All right, so from start to finish, let me see if I can get this all on the same page. Are there any questions about the process we went through for this problem? As you can see, these problems take a while to do. They take a while if I'm explaining every step, but even if you're just working them, they do take a while to do correctly, which means that I have to give you partial credit along the way for doing things. That way, you know, if you can't make it through the entire problem, you're still not just getting a 0 on the problem. So things that I'm looking for partial credit, I'm looking for you to tell me what the constraint is. So here's the constraint. I'm looking for you to tell me what the objective function is. I'm looking for a well-labeled picture. I'm looking for, did you calculate the critical points, right? So all these steps along the way can earn you partial credit. The difficult thing about these problems is if you mess up the objective function, none of the rest of the work will be okay. And in fact, if you mess up the objective function, a lot of times you might create an unsolvable problem, a problem where you can't actually find the maximum or the minimum. And I know that can be frustrating for students because it does put a lot of pressure on you to get this first objective function right. But this is only going to get better by looking at a lot of examples. So I highly encourage you this weekend to go through and work all the examples that are in the textbook. I would encourage you to do the kind of thing where you look at the problem the textbook has, cover up their answer, and then work it yourself and compare that back to the answer that they got. I think there's 7 or 8 good examples in the textbook, and there's another 2 or 3 that I have for you in the videos. And then there's also the online lecture notes as well from another site that have a bunch of examples as well. So dive into that this weekend, and then on Monday we'll come back and we'll look at some of this in a business context. We'll look at maximizing revenue and maximizing profit, and so we'll look at a couple of those business related examples on Monday. All right, y'all have a good weekend.
Have a good weekend, sir.